Hello, everybody. We're embarking on, excuse me, we're continuing chapter 7.1, and we're going to do something called Eigenspace. So if you were interested in space travel or space exploration, we're doing, get it, see what I did there. We're doing Eigenspaces. So let's get the show on the road, and we will start right now. Okay, Eigenspace. So if you have if you have an eigenvalue which has more than one eigenvector, and the truth is you could have infinitely many eigenvectors, really is infinitely many, eigenvectors. So, but let's say you have, one or two of them. Well, if I have an eigenvector x for a particular lambda, well, when I multiply the matrix A times the vector Cx, I can pull the C out of the, out of the equation, out to the front, and this becomes C times AX. But AX, that's lambda X. That's what we've been saying this whole time. That's what eigenvector is. That's what an eigenvalue is. An eigenvector and an eigenvalue. That's what that is. Meaning the matrix A times the vector X equals the scalar lambda times that same vector X. Well, now I can pull the lambda out. I'm not pulling it out. I mean, these are just, C is a scalar, lambda is a scalar, being multiplied by a vector. I could just rearrange it very simply. I get lambda times Cx. So what do we see? What do we learn from this? So we started with a vector x, which was an eigenvector for the eigenvalue lambda. And we noticed that when we multiplied the matrix A times this new vector Cx, we got lambda times that new vector Cx. So this tells us that if x is an eigenvector, then any scalar multiple of x, which means the eigenvectors are closed under scalar multiplication for a particular lambda. Now again, if x1 and x2 are two eigenvectors corresponding to the same, it's very important. The word same here is very crucially important. I'm going to highlight that. We'll see why that is in it very quickly. But so x1 and x2. Now, I'm not saying that x1 and x2 are scalar multiples of each other. They might be, they might not be. It doesn't matter. All that matters is that they're eigenvectors for the same eigenvalue lambda. And why is that important? Well, watch and learn. So I want to show, but my goal is to show that the sum of x1 plus x2, which is a new vector, that I want to show that this new vector is also an eigenvector. So let's do it. So first of all, we learned that a long time ago you can distribute matrix multiplication, and that gives you ax1 plus ax2. But ax1 we know is lambda x1 because x1 alone is an eigenvector, and ax2 is lambda x2. Now I have lambda just a scalar, so I could factor out the lambda, so to speak, and I get lambda times x1 plus x2. But wait a second, what just happened? I took x1 plus x2, which is a vector in its own right, multiplied by the matrix A, and I went up getting lambda times that vector in its own right, lambda 1 plus lambda 2. So that, my friends, is remarkable. But what it really shows us is that eigenvectors of the same eigenvalue, eigenvectors are closed under vector addition and scalar multiplication, which means they form a subspace because they are a, let's just say it officially now. So the eigenvectors of lambda form a subspace. So if A is let's just say it officially, if A is an n by n matrix with an eigenvalue lambda, then the set of all eigenvectors of lambda together, oh, whoopsie, we forgot this, the zero vector. You see, we mentioned that by definition, by convention, we said that zero doesn't count as an eigenvector. But how can you have a subspace without a zero? Vector space has to have a zero. So what we do is we honorarily attach the zero vector to this the set of linear combinations of my other eigenvectors. So So if we take all the different possible eigenvectors of lambda, and we just attach the zero vector to it, we now get a subspace, because we've already shown a subspace of Rn. Well, Rn, as we know, is a vector space, and we've shown that this subset is closed under addition and scalar multiplication, which we have right here, vector addition and scalar multiplication, and power in business. Now, all this is cool and awesome and fine and good, but how do we figure out, how do we determine eigenvalues and eigenspaces and all this kind of cool things? Now we're going to learn numerical or mathematical techniques to do this, but sometimes you can just see it visually, as in the following example, which is coming up right now. Here we go. So in this example, we're looking at the eigenvalues that correspond to the eigenspaces of A, which is -1, 0, 0, 1. So now, what does this matrix do? This is basically the identity matrix with a -1 up on top over here. Well, what that does is that it turns well, you can see it right here. When I multiply this times a vector xy, all I wind up getting is negative x and the same y. That means that my xy got turned to a negative x then y. And visually, here's my xy, that's my negative x, same y. Well, what happened is this is what you call a reflection across the y-axis. So when I multiply A times a vector, it reflects that vector across the y-axis. Well, visually, any vector that I have here, when I do that, it's gonna change directions. What vectors will not change directions? Well, a vector that's on the y-axis itself will not change direction, because it'll just, in fact, it won't do anything. A vector that's on the x-axis, it's going to change. Well, it's not really going to change direction, because it's going to go, a complete 180. So it's going to do a complete 180. And as we said, when you're doing a complete 180, is not considered a different direction. It's just, it's just negative, so it's pointing the opposite way, but it's still in the same, it's still in the same, considered the same direction. So we see from this geometrically, just so visually, I don't know how you want to say it, that any vector that lies on the x-axis and any vector that lies on the y-axis are going to be eigenvectors. Now again, the zero vector doesn't count, but we're going to count it, and we basically have a subspace. This is so this is our subspace. Alrighty, let's meaning to say, I want to be very clear over here. These are two separate subspaces. I mean, the x-axis is one subspace and the y-axis is a separate subspace. Because we learned a long time ago that a subspace of Rn of R2 is either going to be the origin or a line through the origin or the entire plane. Two lines to the origin is not a subspace. Well, two lines to the origin, if anything, it's going to be a basis for the entire plane. But I'm not looking at the entire plane. I'm just looking at these two lines. So wait a second. So I know that, like, logically that the y-axis is a separate subspace and the x-axis is a separate. But how do I say that numerically? Well, let's take a look. Really, see, the y-axis corresponds. The y-axis corresponds to the lambda value, the lambda of 1, the lambda which equals 1, and the x-axis corresponds to the lambda that equals -1. So really, the x-axis is one lambda and the y-axis is a different lambda. And that's the deal. So the eigenvectors that correspond to lambda 1, which is basically the entire x-axis, that forms a subspace. And separately from that, the eigenvectors that correspond to lambda 2, which is the entire y-axis, that's going to form a separate subspace, a different subspace. So we see that each eigenvalue generated a different subspace, so to speak, or the vectors corresponding to each different eigenvalue made different eigenspaces. Anyways, or different subspaces, I should say, of R2. Anyways, this is not always going to be, you know, possible. It's not always going to be possible to get this nice, cool geometrical, you know, visual interpretation. But I just want to show you that sometimes, you know, sometimes we have all this fancy machinery. Sometimes we just take a look with our eyes. Just open. Sometimes you have all these fancy formulas and all these fancy techniques and methods, and I'm gonna teach you all that fancy stuff. But sometimes the solution is just right in front of our eyes if we just kind of look at the picture. Um, very you know, true in general. True in general. Um, so but as the remark over here says, the geometric solution is not typical of a general eigenvalue. It's usually not something we can just look at a picture and figure it out. But and we are going to give you a more general approach coming up. But it's nice if you can see something visually. It just adds something very very wonderful when you can do that. Okay, let me just save this. Okay, now moving back on, and let's go to, so now let's learn how can you find eigenvalues and eigenvectors when you don't have, you know, this beautiful visual, you know, there's how we showed with one problem where you could do it, you know, just visually. What about the other 99.9% of the problems? So let's just look here. This is very important. You have an n by n matrix A, okay? And let's look at the n by n identity matrix I. So this is what we will call IN. It's the n by n identity matrix. Now the eigenvalue equation is that AX equals lambda X. Now, if I just stick a little I in there, it doesn't change anything because I times X is still, you know, it's identity. It keeps it the same. But it's going to help us immensely because, by the way, I times the vector X, what's that product going to be? Is that going to be a square matrix? Is that going to be a column, you know, like a column vector? Well, the answer is it's going to be a column vector because I take an n by n matrix I times the n by 1 matrix X, and remember you take the two outer numbers, so the result will be an n by 1. But we're not done. We still have more tricks up our sleeve. First thing I'm going to do is take the AX and bring it over to the other side. Once it's over to the other side, I'm going to factor out the X, so to speak. So now we have an n by 1 matrix X, and we have here an n by n square matrix because lambda I is a square n by n matrix. A is also a square n by n matrix. So this whole thing is one giant square n by n matrix, and I'm multiplying that times an n by 1 vector. So I wind up getting an n by 1 vector, which will be equal, which, you know, according to this equation, which is going to wind up being equal to the 0 vector, the n by 1 0 vector. Okay, so so this homogeneous system of equations has non-zero solutions. Non-zero solutions. See, obviously, you know, if x itself is just a 0 vector, then, you know, done. But we want to look for non-zero solutions. And that's going to happen if and only if this coefficient matrix lambda I minus A is not invertible. That is, if and only if its determinant is equal to 0. Now, this is going to have, now that's very interesting. This is going to have non-zero solutions if and only if the determinant of this new n by n matrix that I created is going to be 0. So what do you think I'm going to do? I'm going to, given the matrix A, I'm going to construct this new matrix, take the determinant, set that equal to 0, and that's how I'm going to get that's how I'm going to go and get my solution. Let's just do it. I don't know if you're following everything I just said. It sounds like the ravings of a crazy man, but let's just go through it step by step. So let's look at theorem 7.2. So if A is an n by n matrix, an eigenvalue of A is a scalar such that, you ready for this, drum roll please, the determinant of lambda I minus A equals 0. That's exactly what we were just saying up here. And two, and we really just explained why. And two, the eigenvectors of A that correspond to lambda are going to be the non-zero solutions of AI minus lambda I minus A times X equals 0. So that is that's going to be so the non. When I say non-zero, I mean that X won't just be a 0 vector. Okay, so the equation determinant of lambda I minus A equals 0, that equation we have right here, we call that the characteristic equation. And by the way, that's a term we've seen in differential equations, the characteristic polynomials and stuff like that. And again, and there is a lot of, as I said, there's a lot of interplay between differential equations and linear algebra. There's a lot of back and forth, a lot of play between them. What am I trying to say? That's because the typical differential equations that we teach in a first year course, like you take here is really studying linear differential equations. Differential equations don't have to be linear, but a typical first semester college course is, focuses on linear differential equations. So you have a lot of I don't want to say cross pollination between linear algebra course and the differential equations course. Anyway, enough of my pontificating. So when I expand this, you see a determinant, you got to multiply a bunch of stuff out, and you're going to wind up getting a polynomial with lambda. And if I take that and multiply it all out and collect terms and blah blah blah, I'm going to wind up getting this determinant is going to wind up being lambda to the n plus some coefficient times lambda to the n minus 1 plus da da da. So you basically have a polynomial in lambda, and this is called the characteristic polynomial of the matrix A, because because A is really the part that's given, that it all goes according to A. So this definition tells you that eigenvalues of an n by n matrix correspond to the root of a characteristic polynomial of A. And I have to say something, it's a funny thing, because this is like the first time in this entire course. We went through 6 chapters, now we're in the 7th chapter, and we've had very little actual like algebra like you did when you took like college algebra or whatever. We've when for those of you who took differential equations, there's a ton of algebra you have to do. Or any calculus course, there's a ton of algebra you have to do. And but here in linear algebra, we very rarely, hardly ever at all, did any actual old-fashioned algebra. But now, for the first time, we're gonna, because we're gonna deal with solving these characteristic polynomials. Anyway, let's do an example. Everything, as always, everything is always more clear after an example. So we want to find the eigenvalues and the corresponding eigenvectors of the matrix A, which is 2, -12, 1, -5. Okay, now, by the way, if you notice very quickly, the determinant of A does not equal 0, and I never said it had to. We never said that A had to have a 0 determinant. We said that lambda I minus A has to have a 0 determinant. So let's just be very clear about that. Anyways, let's look at this out. So lambda I minus A, well, lambda I just looks like, it's like an identity matrix, but instead of having 1s down the diagonal, you have lambdas down the diagonal. And now I'm subtracting A. So I have lambda minus 2, because I'm subtracting a 2. I have 0 minus -12. That's where you get the that. And I have 0 minus 1. That's negative. That's where I got the -1. And I have lambda minus -5. So I get a lambda plus 5. Now, when you take the determinant, as you know, you multiply these guys and you subtract the product of those guys. So you wind up getting lambda squared plus 3 lambda minus 10. That's just the product down the main diagonal. And then minus -12, so it's plus 12. And this winds up being lambda squared plus 3 lambda plus 2, which factors into lambda plus 1 and lambda plus 2. And as we said, this characteristic polynomial has to equal 0 for this thing to work. So I'm going to take this sucker, set it equal to 0, and guess what? We've just solved for lambda. We now have two values for lambda. We have lambda 1, which is going to be -1 because I'm setting lambda plus 1 equal to 0. Then lambda 2 is going to equal -2 because I'm setting lambda plus 2 equal to 0. So we now have two different lambdas based on this equation. That is totally awesome. Now let's find the corresponding eigenvectors. So what we're going to do is we're going to use Gauss-Jordan elimination, and we're going to solve the homogeneous linear system represented by lambda I minus a times x equals 0. We're going to do it twice because we're going to do it first. We're going to do it for lambda 1, then we're going to do it for lambda 2. So for lambda 1 is equal to -1. So in this equation here, where I have a lambda, I'm going to stick in a -1. So -1 times I, so that's the negative identity matrix, minus the matrix A. Well, that's just going to be -1 minus 2, 12, -1, that doesn't change, then -1 plus 5. I mean, if you want, you could like work it out from scratch. You could just look at this guy here and just plug in -1 for lambda. Either way, you get -3, 12, -4, -1, 4. And you can see that these are multiples of each other. So this row reduces to 1, -4, and then 0, 0 on the bottom. And that tells me that x1 minus 4x2 is equal to 0. Well, instead of saying x and y, we're saying x1, x2. These are the variables. So that equals 0. And if I just let x2 be a parameter t, then x1 is going to be 4t. So the matrix, so x is going to be x1, x2, which is going to be 4t, t. I could pull out the t, and of course, again, t cannot equal 0 because 0 is really not an eigenvector. Even though we made it an honorary eigenvector for certain self-serving purposes earlier, but t times 4, 1, that's my so 4, 1, I guess, would be like the basis, if you will, of this eigenspace, and this is a line through the origin. If I attach the 0, then it becomes a line through the origin. Otherwise, it's a line with a hole at the origin that goes to the origin. Next, now let's go to lambda 2. Lambda 2 is -2, so we're going to plug in -2, and we get work it out, crunch, 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 and we get -4, 12, -1, 3, and that now becomes, again, these are multiples of each other, so that becomes 1, -3, 0, 0, and if I let x2 equal to t, then x1 is going to be 3t. So let's just go up here like that, and pow, and that's my second eigenvector. And in fact, and t, of course, can be any scalar. So there you go. I now have my first eigenspace, which is a line through the origin, parallel to the vector 4, 1, and here's a line to the origin parallel to the vector 3, 1, and there you go. We have our beautiful, wonderful, fabulous two separate eigenspaces, and that, I have to say, is spectacular. This is a nice thing here. Try checking that ax equals lambda x for the eigenvalues and eigenvectors in this example. So I'd like you to pause the video right now and check that this all works. Okay, we're out of commercial. I get it. So let's actually pause here, and we're gonna start from here on the next video. So everybody, it's been a great pleasure, and we'll see you next time.